All right, so my question is it time to rewrite the operating system in Rust? Now, I will give you a little bit of a spoiler alert. This is Betteridge's law of headlines, that any article that kind of asks a question, you can reasonably say no to. So, you're not going to get a no out of me on this one. You're going to get a bunch of qualified yeses, but just to give you a spoiler, it is a question mark, not necessarily an exclamation point for reasons I'll get into. But first, and actually I think it's pretty great that I don't even think I'm the first, maybe not even the second presentation, to have a slide on what even is the operating system. I mean, we're in the OS track. Operating systems have been around a long time, and apparently we don't even know what they are. And it's actually harder to define than you might think. If you think this is easy, by the way, just say like what is software? Give me a definition of what software is. And I can wrap you around the axle on your definition of software. Because I will pose you this follow-up question. Is Euclid's GCD algorithm software? Was Euclid writing software when he wrote the GCD algorithm? And if your answer is like, well, no, of course not, because this predates hardware, it's going to be very hard to come up with a self-consistent answer to what software is. I actually made the mistake. I know Mike Olson, who was one of the founders of Cloudera, and I was up at Cloudera in very early days. There were like 6 people in the office. I don't even know why he had me by. But I was having a weird day, and I was like really grappling with this like, what is software question. And they're like, well, software's the thing that runs on hardware. It's like, okay, well, what's hardware? You kind of take that apart, and everything starts breaking down. Like you are T-minus 10 minutes away from an existential crisis. And you realize that you know nothing, that the ancient Sumerians were running software. That software is merely knowledge that we run. It doesn't have to be Turing complete. And at one point, like Mike can kind of see his team, like, you know, Jeff Hammerbacher, I think, is beginning to like stare at his hands and wonder if anything means anything. And Mike takes me aside. He's like, "What's going on? Like, are you on drugs? I mean, what's like, are you high right now?" I'm like, "No, Mike." I'm just like, "What is software?" He's like, "All right, can you just like talk about something else or whatever, or get out of here?" Anyway. So you have the same problem with the operating system. Like, what is the operating system? Well, kind of like any definition, we would say, well, the operating system is the thing that abstracts hardware. But like, well, how about virtual hardware? I mean, surely abstracting virtual hardware, surely the guest operating system that you run on your AWS instance is surely an operating system. That's not abstracting hardware, not physical hardware, it's abstracting virtual hardware. So it's really easy to kind of migrate around or wander around and not have a really concise definition. But I think for our purposes, let's say that an operating system is the program, because it is a program, that abstracts the hardware to allow for the execution of other programs. So I think that the fact that the operating system is itself just a program, it's just kind of a super program, is kind of an important observation. My friend Mike Demmer, who's here, went to work for a company called Terra that you haven't heard of. Terra actually bought Cray and then took Cray's name, which is always an interesting sign. When the acquiring company takes the acquired company's name, you know it did not have real good brand recognition. But Terra was a super interesting company doing lots of interesting things, and Mike was doing kernel development for them, and had done that for maybe a year or two, and he and I caught up, and he's like, you know what? I realized that an operating system is really just a program. It's just a complicated program. It's an asynchronous program. It's an interrupt-driven program. At the time, I was kind of offended by that, because I'm like, I'm not just a programmer, I'm a kernel programmer. Like, don't rob me of my dignity. But then you realize, like, actually, it is just a program. It's a complicated program. But it's a program that runs other programs. I do think that if your program doesn't run other programs, it's a lot of great things that's valuable to society and humanity, but we probably shouldn't call it an operating system. And I think that the operating system also should be abstracting hardware in some way, shape, or form, but even that there's shades of gray there. And I think the operating system, you have to say, defines the liveness of the programs that it's running. If the operating system dies, everything that it's running dies. Can't live without the operating system. So it's essential in that regard. It's important not to conflate the operating system with the operating system kernel. The operating system kernel is the thing that runs in the privileged context of the microprocessor. That's going to be ring 0 if you're x86, although ring 0 becomes complicated because if you're in virtual hardware, you're in a virtual ring 0. Nested virt, you could be in ring 0s, that's several rings away from the actual hardware. But you are in, whether it's virtual hardware or physical hardware, you are seeing the entire machine, or what you believe to be the machine. Virtualization has made this so complicated. Like, everything has to have asterisks now. It was a lot easier when we weren't virtualizing hardware. But the operating system kernel is only one part of the broader operating system. The operating system also includes libraries. It includes commands. It includes daemons. It includes facilities. And yes, Justin was in his earlier talk was describing how we want to strip all this stuff away. He blamed it all on Sun somewhat strangely, and then said that we needed to strip it all away. And that is true to a point, but there's still, even in Justin's stripped down world, there are still a bunch of components that aren't running at that highest level of privilege on the microprocessor or virtual microprocessor, but we would still consider the operating system. So the operating system is bigger than just the kernel, and I think that's really important. Now, I mean, if you've seen me talk before, you know there's no way we're getting out of here without a history lesson. And especially when we're talking about operating systems, we've got to turn the Wayback Dial, and we've got to talk about history. So operating systems were actually, they used to be called executives, which is a very kind of like strange post-World War II hierarchical kind of like, I'm not sure, you know, there's like a managerial structure. I guess executives, I mean, there are things that could have been worse, but we had executives for a while, and they changed it to operating systems. And originally, these things were all written in assembly, of course. They were all written in machine code. And if there's one really interesting architecture to look at, it's the Burroughs B5000. 1961 was a super interesting machine, and that was the first operating system, which was called the MCP, which is the Master Control Program. Yes, if you've seen Tron, it's a master control program in Tron. If you haven't seen Tron, do not see Tron. It is a terrible, terrible movie. Go see War Games instead. So you're trying to catch up on the movies you missed because they happened 20 years before you were born. Go watch War Games, not Tron, please. But MCP was the Master Control Program, Master Control Executive, just like all about dominating programs, I guess. But the thing that was really interesting is this thing was written in its own algol derivative called SBAL. And if SBAL, I just feel like I get Esperanto in my head immediately when you say SBAL. And SBAL, as it turns out, is a not to be confused with a university in Ecuador whose abbreviation is SBAL. So probably a much more famous SBAL at this point. But SBAL was this algol derivative that they wrote the MCP in. And this was a machine that was way ahead of its time in many different dimensions. And I can tell you, as a technologist who has had the misfortune of being ahead of my time several times over, being ahead of your time is not commercially fruitful. Basically, the biggest upside of being ahead of your time is you apparently need no introduction to the OS track. But other than that, it's all. So Burroughs is a machine was a wildly inventive company, incredible machine, but you haven't heard of it because they went out of business. But the MCP was really interesting, and then in 1964, Project Mac at MIT was looking to build a follow-on for CTSS, which is the Compatible Time Sharing System. And they wanted to do everything right. Now, this is something we call second system syndrome. And second system syndrome, every time I think second system syndrome is a bit invented, and maybe it's a relic, maybe it's kind of a mythical man month, kind of holdover from the 60s, I get hit by another second system. So I think it is a truth. A second system syndrome is, hey, as long as we're going to rewrite this, we should also rewrite that and revisit this and redo. We should finally do this the right way, and let's do that the right way, and let's finally change the database to be something. And next thing you know, you have this massive system that ships later and later and later and later, and finally never ships at all. And that's the second system syndrome. Project Mac had maybe the case of second system syndrome with Multix. And Multix, and then this is also just a misfortune of history in terms of when they came along. They knew they wanted to do it in a higher level language, but I guess they just didn't like the higher level languages that were out at the time. Now, on the one hand, according to Multix, like, well, the only things to pick from were really Fortran and COBOL. That's actually not the case. So someone you probably haven't heard of named Jean Sammet was an early computer scientist, and she wrote an incredible book called Programming Languages, which is a taxonomy of programming languages circa 1963, whenever that book was written. And let me tell you, that book is more than 2 pages long, okay? Like, there were a lot of programming languages, maybe too many programming languages, like a Mesozoic era programming languages, too much CO2 in the programming language atmosphere or something, 80-foot tall ferns or whatever. But there were a lot of programming languages to pick from, but whatever, they didn't like them all, so fine. So we're going to do it in this programming language that hasn't yet been implemented, but has this really amazing specification called PL1. So they did this in PL1. That is a Roman numeral 1, by the way. If you want to put PL1 in your own slides, do not call that that is not an Arabic 1. That is a Roman 1. Very important point. And so they adopted PL1, and then they wrote the full specification for Multix with not only not a line of code, not a compiler. They didn't have a compiler. In fact, they decided, I don't know, why do you do this? They let's outsource the compiler. It's like, okay, that makes sense. Let's outsource the first PL1 compiler ever to be written. We're going to outsource this to this group in Los Angeles that no one had ever heard of, who, shows you how some things never change. They were like, sure, we can implement a PL1 compiler. And then, a year later, they kind of fly out and be like, where's the PL1 compiler? They're like, we don't know what we're doing. We cannot, we cannot implement a PL1 compiler. So all right, well, we have no PL1 compiler. So, but we have an amazing operating system that has been very detailed, very specified, but we can't actually write any of it because we don't have a compiler. So this is ultimate waterfall, nightmare waterfall. And so they didn't have a PL1 compiler until 1966. And that is a major problem. Now, the thing is really funny about Multix, and Multix is one of these things that's a super divisive history, in that depending on who you talk to, Multix was either this amazing success that no one gives adequate credit to, or this dismal failure. And I'm sure the truth is in the middle. But Corbato wrote Corbato, I guess, wrote an interesting piece, Multix the first 7 years, in 1971, after Multix has already kind of failed-ish. A bunch of companies had pulled out of Multix, and they viewed PL1 as being this great aspect of Multix, and there's no real mention of the fact, well, you didn't have a compiler for 3 years. I'm not sure that it's an unabashed success, because to me, and again, it's hard because this is all before I was born, it's hard to know for certain, but to me, looking back on it, the fact that the compiler was not available for so long had to have exacerbated the decline of the coalition. They actually called them the triumvirate that ran Multix. And in particular, Bell Labs pulled out of the Multix project. So Bell Labs is like, all right, we're done. This is crazy. This is not going anywhere. The compiler hasn't shown up. It doesn't work. They actually didn't, because PL1 wasn't there, they developed a different dialect of PL1 called EPL. And this is another thing, you read what the EPL people say, and they're like, boy, did we save the day. We came up with this dialect of PL1 called EPL. Then you read Corbato, he's like, people came up with the dialect of PL1, but we never used it, and it was completely insignificant. So it's like, all right, I've got no idea what happened. It's like watching Rashomon for operating systems. Anyway, Bell Labs pulls out of Multix in 1969, and there was a researcher that was formerly on the Multix effort, guy Ken Thompson, you've heard of presumably, who wanted to implement a new operating system, and now didn't have Multix, so implemented this thing on the PDP-7. It was later ported to the PDP 1120, and it was named Unix as a wordplay, if kind of a somewhat peculiar one, on the complexity of Multix. And every time I kind of reread the Unix history, I get kind of something different out of it. It's unquestionable that Unix, a lot came together at Unix in terms of the late 60s, especially the early 70s. They were in the right place at the right time. One of the things that I see, especially reading it side by side with the Multix history, is it was really top-down software versus bottom-up software. And Multix was very top-down, command and control, write the specification, maybe we'll get a compiler, maybe we won't, kind of software. Unix was like, let's just get something working, and then, I don't know, get something else working, and then we'll write a man page for whatever we already got working. And it was very organic, and I think that the world was ready for that kind of software model. And you begin to realize, kind of, looking at it in the larger lens of what was going on socially and everything else, as my mother is fond of reminding me that because I wasn't alive in 1968, I've got no idea what a society on the brink actually looks like. Every time I complain about the president, she's like, oh, this has nothing compared to 1968. I'm like, all right, Mom, fine. Mom, you're kind of confirming the stereotype of baby boomers, but let's move on. But in particular, Unix was implemented entirely in assembly. And I think it's a bit of a myth that Unix was implemented in C. It wasn't. It was implemented in assembly for the PDP-7. It was ported to assembly on the PDP-11. And yes, there was B. There was this interpreted language that was B that was around. It was a BCPL derivative. B had there's a very kind of like strange kind of connection to Multix in that B and EPL were both implemented in this thing called TMG. TMG, I know that sounds like a teen web series that my kids would watch. I feel like I would, like my 14-year-old would be watching the latest episode of TMG, but no, TMG was the transmogrifier that was a transpiler, and B was actually interpreted. And actually TMG, another kind of, footnote on a footnote, was implemented by Robert Morris, Bob Morris, the father of Robert Morris Jr., who was the Morris worm, even though I think Paul Graham begins to like his eye twitches when everyone says the Morris worm because he and Robert Morris founded a company together. He doesn't like anyone to talk about the Morris worm, but it's fine. I thought it was anyway, whatever. Tangents on tangents. But so B actually was only used in these like super auxiliary capacities in Unix. And it was used in the assembler. It was used in an early version of DC. DC, a command that you only may know from mistyping CD. You ever done this where it's like, you want to like CD to your home directory or whatever, you just like CD enter, you're like DC enter, and you're like, wait, what just happened? And you're like a captive prompt, and you're like, Control C, and it's like, eats the Control C. You're like, what is going on? You're like, Control D, like quit. You're like, I don't know how to quit, or whatever it says. It actually doesn't say that. It doesn't actually say anything. DC is it reflects its B heritage, suffice it to say. But so they realized that B was not going to do it. It didn't perform. They needed a much higher performing language than B. In particular, Dennis Ritchie and Ken Thompson, saw the power of implementing the operating system in a higher level language, but they knew that B in particular had no byte addressability. So the lack of byte addressability was going to be a big problem. So they came up with a new language that they called C. And so C followed on for B, it made sense. But again, contrary to the myth, they are not twins. They're not born at the same time. Unix begats C in a very important, I guess, biblical way. Their siblings they're not twins, and Unix is very much the older sibling. And so C is rightfully called portable assembly. I like the people call C portable assembly as a slur, but I view it as praise. Wow, it's assembly and it's portable? That sounds great. There's a lot that is great about C. And C also was way ahead of its time. And if you look at those other programming languages from that era, and then you look at C, it's like stepping into modernity suddenly. First of all, the caps lock key disappears. It feels like every language prior to C was like screamed. It's like, was the caps lock key broken? And you know, I like to collect old programming manuals, and I bought a kind of a weird lot from someone in the UK, and this box shows up, and it's like a bunch of crap. And then there's this manual for this language called Language H. And Language H is a COBOL derivative that you've not heard of for a reason. This is an NCR Elliott-initiated language that had Sterling as a keyword. Every Language H program begins with chapter 1. And you're like, oh, okay, all right, this is cool. Like, it's a book. Like, I get it. Like, whatever. It's like super new. Computing is super new, and a book is the best analog. And then you're like, chapter 1. It'll be like, you know, Sterling, and they talk about tapes and all these kind of calculations. And then every program, there's no chapter 2, by the way. It's only chapter 1. Every program ends with the keyword obey. And you're like, what? Like, how about epilogue or end? Like, that doesn't make any sense. It's like now all of a sudden these are like orders that you're, anyway, whatever. It doesn't make any sense. So that's what we got. We went from like obey and chapter 1 to modernity kind of in a very short period of time. And the C revolution was real. And it was organic. I mean, I think one of the things that's interesting, again, if you look at this Multix as this top-down approach, this kind of command and control approach, and Unix as this more bottom-up approach, one of the differences you see is that C kind of grew things as it needed them. The first implementation of C didn't have structures. They added, now admittedly, structures were added in 1973. This came in early. But they didn't actually implement the Unix kernel in C until they had structures. They implemented structures because they needed them for the Unix kernel. They implemented bit fields because they needed them for the Unix kernel. So they implemented things as they needed them, which had strengths and weaknesses. One of the weaknesses from my perspective, there is no logical XOR in C. This is one of the things that pisses me off about C. I know this is an arcane thing to get kind of spun up about, but there's no logical XOR. You've got bitwise XOR, and you've got bitwise and bitwise OR, and you've got logical and logical OR. So where's logical XOR? And there are actually times when you want logical XOR in C, where you want to assert one of these conditions is true, or the other condition is true, but not both of them, and at least one of them. Like, that's logical XOR. And you'll know you're in my code because that code has that assertion, yes, done with bitwise XOR. I know how to do it, okay? With an extra line of code and then a block comment, like cursing the ghost of Dennis Ritchie for not having logical XOR. Even more galling, actually, was I worked with a guy, Roger Faulkner, who worked with Dennis Ritchie, and I was complaining about this. He's like, no, there's no logical XOR because logical XOR can't short circuit. And I'm like, Roger, I know that logical XOR can't short circuit, but like, is there some sort of biblical commandment that logical operations must be able to short circuit? He's like, no, I'm just telling you that that's the reason. I'm like, that's not the reason. He's like, well, I'll ask Dennis. I'm like, go ask Dennis, do it. And of course, Dennis immediately replies like, no, we don't have logical XOR because it can't short circuit, and you should just use bitwise. I'm like, nah. Anyway. So I was wrong. But so there was this kind of organic growth. The organic growth was important. In particular, C grew very important facilities like macro processing. Macro processing and Rust has actually caused me to reflect back on my own use of macros, because it's one of the things I absolutely love about Rust. The macro facilities in C are really, really, really important. Yes, I know you've been told never to use the preprocessor, and yeah, I get it. But like, that's the same thing like we tell our kids about like, that they shouldn't, drink and they shouldn't do drugs and they shouldn't have sex and all sorts of other like fun stuff that like actually they should do when they get older and they can do so safely. Like I want grandkids, like I mean at some point like figure it out, but not now. The preprocessor is the same way. The preprocessor is really essential. It was essential for us in dtrace. It was essential in CFS. It was essential for a lot of the things we've done. But the preprocessor leaves a lot to be desired. There were standardization efforts, but they came late. They were contentious, and so on. So through the 80s, C just dominated. It was an excellent fit for operating systems. Essentially every OS, with some exceptions. I know the Mac was in Pascal, fine. So there's going to be one of those in every class. And there were some research operating systems. I don't imply this is the totality of operating systems, but the vast majority of production systems were either in C or they were still in assembly because they were DOS. Many of them were in C. In the 1990s, a great darkness came across the land. It was really a terrible time to be alive, I'm convinced. And now I can speak from personal experience. It really felt very, because object-oriented programming felt like there was this kind of this industrial complex, object-oriented industrial complex that insisted that everything be object-oriented. And the C-based systems were thought to be relics. Everything was going to be, any C-based system was the Walking Dead. And this is all going to be replaced by these beautiful C++ systems or Java-based systems that are going to replace all of this. So you can keep working on this legacy garbage if you want, but all of us are going to go over here. All of the flowery people are going to go over here. The architects are going to architect this great beauty. And all of those systems failed. And they failed, I think, for a bunch of reasons. But one is they were all framed as second systems. And a lot of them suffered from the second system syndrome. So Apple's Copeland. I mean, kids grow up today and they think of Apple as the $1 trillion company. I still remember when Gil Amelio was running Apple, and every other Silicon Valley company was eyeing them for their real estate. Because they couldn't ship an operating system. They had this second system called Copeland. It was going nowhere. Sun had Spring that was written all in C++. I was an undergraduate at the time. We got this hot release of Spring. You thought we were getting like something that was like illegal. I mean, it was like, okay, I'm going to give this to you on a CD, but it's amazing. And you run it, it's like, is this a hard drive stress test? Because all this thing is doing is rattling the spindle. And it's just that they're like, well, how much DRAM do you have? And at the time, this is a souped up machine that had 32 megabytes of DRAM. And they're like, well, oh, no, that's not nearly enough DRAM. You need to have 128 megabytes of DRAM. Which is like saying today, oh, you only have 512 gigs of DRAM. Yeah, you're going to need like 2 terabytes of DRAM. And you're like, who has that? Like, well, all of the Spring developers have that. Like, that's a bad idea. Like, do I need to tell you that that's a very bad idea? To give, you don't want to give your OS developers so much memory because they'll use it all, and then it can't be used on a system that's got less memory. Anyway, so there was on Spring. There was have you ever heard of Taligent? Oh yeah. So Taligent was going to rule us all. So Taligent was going to. It was IBM and Apple. It was the best and the brightest were going to go up to the ivory tower and hand us down the operating system that we would run. Taligent, as it turns out, actually didn't learn that. Thankfully, I didn't know this at the time. I might have really gone nonlinear. Taligent, as it turns out, is a portmanteau of talented and intelligent. It's like, woo, boy! It's like, how about Airhole? How about that? Like, that's call your company that. And as it turns out, they like nailed the worst of IBM meeting the worst of Apple in an effort that was a total disaster. And they were going to do this kind of operating system, and it wasn't necessarily their fault. It was like because they were taking this from scratch approach. It's just that it attracts all sorts of abstraction garbage, like some sort of terrible abstraction fly strip. So, and then the Java-based operating systems. I mean, I was at Sun, so I'm obligated to remind us all that Java OS actually went nowhere. This is where we're going to do Java everywhere. We're going to do Java-based microprocessors. We'll do a Java OS. Java had no unsigned type. Hard to talk to hardware when you have no unsigned type, as it turns out. So that didn't work very well. But then Linux arrived. And the nice thing about Linux, especially x86, is that Unix had a huge resurgence. But with that, C-based systems became really deeply entrenched. And there were a bunch of C++ efforts. They all kind of withered. And there are exceptions to this. Haiku is an exception to this. But when Haiku is listed as your example of a serious attempt, I mean, I love Haiku, first of all, but Haiku was designed as like the hobbyist operating system to emulate B. It's great, I love it, but it's the counterexample. And again, I'm sure there are others, but basically C++ kernels withered, everything was in C. And at the same time, there was this kind of era that was very kind of hegemonical around Java and C++, but especially Java. And then appeared other languages. First Ruby, and then Python, JavaScript. JavaScript has, if you look at the popularity of JavaScript over time, there's kind of this dip where JavaScript was used to for blank tags or whatever. And then in 2006, I, like a bunch of people, realized wait a minute, there's a language on the browser. And okay, I've got to use it because I need to build something that's going to be this kind of web app. And I, again, I think a lot of people waited in the JavaScript and realized this is a real language, actually. This actually is Lisp in disguise in the browser, but with no parentheses. And I kind of hate the parentheses, so I'm fine with that. And so JavaScript was super interesting, and there were lots of things that were interesting about that. But all those languages really focused on the developer in development and the speed of development, the pace of development. I cannot bring myself to put developer velocity on a slide because it makes me want to throw up. But that is what we were trying to do. That is what we're trying to do. We're trying to make developers faster. But there wasn't, I don't think, if there's a Ruby OS effort, or a Python OS effort. It's like, okay, maybe there was. It's like Steve's like, oh my God, we promised never to speak of the Ruby OS effort. Exactly. A lot of mistakes were made. I was experimenting. It was age appropriate. That makes total sense. But there would be a lot of problems making a Ruby OS or a Python OS, and it would be something you would do because you were in college, which is fine. But there were no real serious efforts. So we hit kind of, I guess what we're going to end up calling the teens, which makes no sense to me, but we hit the 2010s, and system programmers were looking for something different. We want the performance of C, but we had used these other languages, and it's kind of nice to use a map or a hash, or it's kind of nice to be able to use to use split or regular expressions or what have you. Things that are powerful constructs, but I want them in the system that I'm building. And there were kind of some interesting things that came out of that. One of them, I'm a joint, and so one of the things that was an interesting artifact around that is that there was a JavaScript war in the browser, which led to some very powerful JavaScript runtimes, V8 in particular, that we could actually run on the server, and actually we could run reasonable servers right in JavaScript on the server side, Node.js. And that was really interesting. Now, as it turns out, that left a lot to be desired because it's still JavaScript. I mean, I love JavaScript, but JavaScript is the failed state of programming languages. In that JavaScript wants anything to go, wants to allow so much that it can become difficult, and things like TypeScript kind of came into that gap and so on. But JavaScript wasn't necessarily it. We used it a lot of Joint, but there were lots of challenges in the broader world for system software. The Bell Labs refugees at Google I'm not sure if they like to be called that or not. I mean that as praise, not damnation, but developed Go, of course. Many people use Go. Go definitely solved some of these problems, but there are some idiosyncrasies. I tried to put that in the best possible way I could. There are some idiosyncrasies. If you didn't see it, Aiden's had a great talk earlier on gvisor and some of the I would say both the promise and the peril of Go for a very creative use case. One of the problems with Go from an operating system perspective is that Go and JavaScript and others are GC'd. They're garbage collected. And they are very, I mean, speaking for V8, because I know V8 better than Go, it's very sophisticated GC. I mean, it's very sophisticated garbage collection, but it's still garbage collection. And garbage collection, even when it's sophisticated, it's not the garbage collector. People like to blame the garbage collector. It's like, the garbage collector is ruining my process. It's like, no, the garbage is ruining your process. Like, you're creating the garbage. It's not like the GC hates you. It's just like, stop creating crap and the GC won't have to do this. Or worse, stop creating these huge, I mean, when the GC is really exhausting itself, it's because you have a memory leak. It's like, but I can't have a memory leak. It's GC'd. It's like, oh, this is exactly how we got here. But because what you have is a big object graph that's very connected. And in JavaScript, it's very easy to accidentally have a closure that has a reference into this big object graph. And now none of this can go away because it's not garbage. It's not a garbage collector. It's a heap scanner. And it's not finding it. It's scanning your heap very well. Thank you very much. And this is tough. This is just tough. And it makes it, like GC, I honor GC. I think it's great for a lot of software, but there's a class of system software for which GC just doesn't work. And it doesn't work because you don't have predictable performance, because the latencies can be significant, and because it doesn't force the programmer to really think about this stuff. And I think thinking is important for, wait. That sounds pejorative, the way I'm going to phrase it, but I don't mean this pejoratively. I think there is a class of software for which I don't mind requiring deeper thought up front. And then there's another class of software for like, hey, let's get something working, and that's fine. So this is not like the entire world should be GC'd or none of the world should be GC'd. I actually do think there are right tools for the job. But for system software, for the operating system, for that infrastructure, I think GC is a real problem. And at least for me, like I am at the point where it's like I don't want to do performance critical software in GC. And then, so I was actually at a bit of a quandary because like the node thing like wasn't working out. I was kind of getting out of a bad relationship on that one. And then it's like, what's next? And like C++, I had done way too much C++. I talked about in college, I had done way too much C++. So Steve had done RubyOS. I had written 100,000 lines of C++. They were both age-appropriate mistakes, I think we would say in retrospect. I didn't want to go back to C++. And I was like, no, but C++ is like totally changed now. I'm like, that's great for C++, and I want C++ to have a happy and productive life. But C++ dragged all my shit into the street and lit it on fire. So like, I am not going back to C++ ever, and that's not a value judgment. That's just like, that's self-preservation. I'm not going back to C++. So forget C++. It's not going to be C++, even though, again, I honor the changes they made to it. And kind of like looking at this, I was getting increasingly excited about Rust. Rust was really interesting. And I think, how many people are aware of Rust? Okay, a lot of hands. How many people have kind of pined after Rust but haven't written any? Okay, how many of you actually written Rust? That's a good number, actually. Yeah, I think it's a good number, right? Yeah, it's a good number. But okay, but a lot of you were in the category that I was in not that long ago, which is kind of like I was seriously Rust curious. I was like reading all the blog entries and kind of like, looking like, wow, like that looks interesting and this looks interesting, and like, but what do they do about white space? Because I gotta find a reason to hate it, which is wrong, right? You don't want to do that. Like, get over your white space. This is why I've learned a tough lesson. But like, I was really interested by it. I was intrigued by Rust. And in particular, the values of Rust really represented the values that I have for my own software. So values, in terms of the values of Rust, said very upfront, you go to any Rust website, it's going to say that it is a system software language that runs fast and is designed to be safe. And that was really interesting because those are the things that I want to do. And I want to build permanent software. I want to build software that outlives me. I've already written software that I know absolutely will outlive me. And not because I plan to walk in the traffic tonight, but because there is software that I've written that's simply going to be uneconomical to rewrite because it works. And the thing that is beautiful and amazing about software is, like Euclid's GCD algorithm 2,000 years ago, when software works, we've always focused on how software is always broken and the world is terrible, which is fine, that's true. But when software works, it works forever for the problem that it's solving. It is mathematical machining. I mean, we are really lucky because most of us are software developers, and we are lucky to be alive now. We live in a golden age of this stuff. Our descendants will look back at this time as this just like amazing time when all of the software was being written. And now that said, some of the software is not going to last forever. Some of the software we are going to have to rewrite with software that can survive in perpetuity. And what I see from Rust is that aspiration in perpetuity. And I know Rust has like 8 different origin stories, all from Graydon. I mean, Graydon came up with the name and has got like 8 different reasons why he called it Rust. But the one that I like is that I like kind of that industrial sense of building things that survive, such that the chemical reaction with the oxygen is like your biggest problem. That's pretty neat. So Rust is really interesting. The thing that is super interesting about Rust, and to the best of my knowledge unique, is the notion of ownership. So Rust is able to statically figure out who owns what. And when you being like the thread of control, own the memory that you're dealing with, and when you don't. And when you don't, when you're done, when it realizes like, okay, you're done with this, I will take care of freeing this for you. There is no free in Rust per se. Memory is allocated for you, and then it is freed when you are done with it. Now that is the compiler makes this huge bargain with you. It's like the compiler says to you, I will do this for you. I, the Rust compiler, will do this. I will give you this incredible superpower where you don't need to think about this, but you're going to need to help me out. And you're going to need to help me out when I don't know where this memory is going or who owns it. So I'm going to allow you to lend this memory out. I'm going to allow you a caller to borrow it, right? But I need to know when it comes back. And sometimes I get confused. I, the compiler, get confused. And sometimes it uses lexical lifetimes a lot to figure out like what owns what when. And sometimes I will give you an incredibly cryptic error message because I am confused about who owns what when. And you are going to grind on this to get this working, even though it feels painful and it feels like I'm giving you mixed messages and telling you to like fetch rocks, because I'm going to do this incredible thing for you where I'm going to give you the power of a garbage collected language with the performance of manual memory management. And that's amazing, and it's really important. And it's important for different people for different reasons. So there is a demographic, probably a big demographic. There are a lot of folks for whom it's like, the great thing about that is memory safety. That I can't overwrite anyone else's memory. And that is really important. I'm not going to have B zeros that have got the wrong size on them, mem copies that have the wrong size on them. I'm not going to, one of the things I love about Rust, among other things, is Rust, there's lots of kinds of data corruption that Rust prevents. One thing is, when you initialize a structure, you have to initialize all fields. And on the one hand, you're like, hey, Rust, get out of my grill. Like, why do I have to initialize all of these? And Rust should be like, what's your problem? Like, why don't you want to initialize this? Like, you're the one with the problem. Like, you initialize this. Give me a value. Like, if it's b0, put a 0 there. Fortunately, like, the Rust compiler doesn't like get that belligerent with you. In fact, actually, what's really funny is like the Rust compiler has like such a fearsome reputation for somewhat legitimate reasons, just because when the borrow checker is angry with you, it can feel like I don't know what to do. So as a result, the Rust compiler totally overcompensates and is like the friendliest compiler I've ever encountered because Rust is like, oh, I don't think you meant this. I think you might have meant this thing. And like, here's exactly what, and like, look, I got all these ASCII colors where I'm showing you exactly where it is. And you're like, why are you being so helpful? This is great. It's like, just remember this later, okay? Just like, remember my helpfulness at your darkest hour, because your darkest hour is probably coming. But I actually do. I love the Rust compiler. And the reason this is important is, for me, memory safety isn't as big of an issue because, and this is going to sound, I don't want to sound arrogant, but this is like, I can write correct C. And now I've gotten it the hard way. It's not something that I would recommend for everybody, but like I can write correct C. And I've written a lot of correct C. I can write C that frees memory properly, that doesn't overwrite, and that basically doesn't suffer from memory corruption. The arithmetic overflows are a lot harder, actually. Rust actually helps you with that. That one I'm not going to make the claim because those are super hard. But on memory safety, I can do that. But Rust is still valuable for me because I can do that because I'm controlling heaven and earth in my software. It makes it very hard to compose software. Because even if you and I both know how to write memory-safe C, it's very hard for us to have an interface boundary where we can agree about who does what. So you know how to free memory properly, and I know how to free memory properly. Oh, but I didn't realize that in that error condition, I was supposed to free the handle that you had given me, not you. Or it's a miscommunication. And it's really easy to do. C is very, very hard to compose properly. And one of the things that we do a lot, actually, to compose C is we use something called intrusive data structures, where you embed nodes of a data structure in your larger structure, which is great for C. It's terrible for Rust. We'll talk about that in a bit. But Rust it allows you to actually compose, truly compose. Because you don't need to worry about, the borrow checker has assured that the contracts for who owns what are implicitly abided by. And it's amazing. It really is amazing. Because you can build these really sophisticated primitives. And in my experience, and again, everyone's mileage may vary, and I'm not trying to, I had this blog entry comparing the performance of Rust to the performance of C for my application. And I had these 8 paragraphs trying to explain how this is not trying to draw broader conclusions about the performance of C versus the performance of Rust. But of course, it's the internet. So the first comment is I can't believe this jerk thinks that Rust is always faster than C. It's that's not what I'm saying. For the software that I wrote, I had a body of software that was in C. It was a C and N node. I rewrote it in Rust. And when I rewrote it in Rust, my expectations were, well, I should say when I was doing that, I was almost inhibited by the fact that I was effectively porting my C, because I tried to do some of the things the same way I had done them in C. And in particular, in C, we have multiple ownership all the time. So when a doubly linked list is actually 2 linked lists, right? And a given object is actually owned by 2 things. The thing, your next thing and your previous thing. They both think they own you. Rust does not want to do that. I mean, you can do it. And there's a great blog entry, a series of blog entries on, so you really want to write a doubly linked list in Rust. You really don't want to do it. And what you want to do is, with Rust, and I think, and the whole Rust community I think has been very upfront about this bargain that you're buying into with Rust, is you want to rethink your problem and implement it in a way that makes your ownership clear. So if you convey your ownership clearly, Rust will give you very high-performing code as a result. It's OK, I can buy that. So I had done so many things. I've got 5 minutes until we're done. Woo, boy, that went fast. All right, we're going to pick up the pace. That's for questions. I'm not taking questions. That's fine. All right, whew, false alarm. I thought it was a false sense of time. But in my experience, so I went to go implement this thing in Rust. I'd made all these compromises because I just got to the point where I got so beaten down. I mean, beaten down, that's too violent an expression. But I was bargaining. I was in the bargaining phase. I'm I will do anything to get this working. I need to get this work because I was trying to make it high performing and do what I'd done in C. I'm I need to stop doing that. I just need to get this damn thing working. So I got it working, and I'm I don't think it's going to have anywhere near the performance of C because the way I did it was so dumb. I mean, it's I just did it the knuckleheaded way. I implemented a doubly linked list effectively by having hash tables of UUIDs, where I'm constantly you want to get your next one, you got to look up this UUID effectively, this timestamp to get to the next thing. And I'm this is terrible. This is going to perform abysmally, and it outperformed my C. It's outperform, what the hell? And so I'm all right, I got to take that apart. What actually happened? What actually happened is, and it gets right to the composability of Rust. What actually happened is this particular code spends all of its time searching in a data structure, in a sorted data structure. which in my C implementation was an AVL tree for a lot of good reasons. We use AVL trees all over the place because they're super easy to use. You can embed an AVL node in your broader C structure. You can have a given C structure that's on 15 different AVL trees at the same time by embedding different AVL nodes. We've got a library that gets it right, and and so on and so forth. So there's a lot of good reasons to do it. But an AVL tree is actually not, it's good, but it's not the best data structure to use. And in particular, Rust uses B trees. And B trees, yes, from databases. Rust implements data structures. Its binary tree structure is a B tree. As it turns out, in this era, in the memory hierarchy being what it is, cache line sizes being what they are, a B tree is actually a better implementation. And the implementation for B trees in Rust is total rocket science. And there's some great blog entries describing the kind of the iteration on that. But it's amazing stuff. So a lot of this is a lot of the performance delta here, and this is runtime on the y-axis, and the rectangles kind of varies the data set size effectively for this particular application. A lot of the win, on the one hand, was B trees, and it'd be easy to be like, wow, that's B trees, not AVL trees. It's like, yeah, but the reason I could use a B tree and not an AVL tree is because of that composability of Rust. A B tree in C is gnarly. And because a B tree is just, talk about intrusive. It's very intrusive. It's very kind of up in everything's underwear. And someone, of course, the internet is like, well, you should go to use this B tree implementation. You look at the B tree implementation, like, this is rocky. And if this thing if there's a memory corruption issue in here, I do not want to have to go find it. So I would still use an AVL tree in C, even though I know I'm giving up some small amount of performance. But in Rust, I get to use a B tree, which is really amazing. Now, beyond ownership, there are tons of features in Rust that I love. Algebraic types allow for amazing error handling. So algebraic types say, this is a thing that can be a this or a that or this other thing. But it's only one of these things. It's basically like a union, but a C union, but with really first-class support. And the great thing about Rust is if you return a result that is one of these things, you need to figure out which one of these things it is. Is this an error? Is this an actual thing that I can unwrap? And it's beautiful. It really results in terrific error handling. We can go into more details, not now, but you can find that online. There's a terrific chapter in the book on error handling. Hygienic macros. I so didn't have hygienic macros in C that I kid you not, I did not know how to spell hygienic until I wrote a blog entry on this like 2 months ago. Like, I literally did not know how to spell hygienic as a C programmer. It's like that extra I. What's that doing in there? But the hygienic macros, that is, say macros that I can actually get into the abstract syntax tree, are a first-class primitive in Rust, and it's amazing. You can do crazy powerful stuff in macros. Crazy powerful, safe stuff in macros. The foreign function interface, which is so difficult with GC languages, right? With GC, a point I should have made earlier when we talked about GC languages, part of the reason they are an ill fit for an operating system is because it's very hard to have C code that lives beside G seed code and can actually share objects across them. The foreign function interface in Rust is very well thought out, very full, and supports, I kind of invented this term, I'm sure there's a better one out there, full duplex integration, and that you can take C and drop it into Rust, or Rust and drop it into C. And that is really interesting. And there's a lot of, I'd say, community interest in that. And one of the neat things about Rust is that there's an unsafe keyword that you can use for unsafe operation. It's not arbitrary operation. You can't just have the unsafe keyword and then just go to town. So there are certain things though that get relaxed when you have this unsafe keyword, which allows you to overrule the safety guarantees just ever so slightly where you need to, though with obvious peril. But in particular, that allows you to build composable data structures that can be used by other things. So, and there's a ton of other great features. But also, there's actually Steve in the room. It's a terrific community. It's a terrific community if you're not in the room. I didn't mean to imply that it's only a terrific community when you're in the room, but the Rust community is actually really amazing. So if you are in, and I got to the point where open source communities just kind of give me a throbbing headache because it can be really difficult to accommodate, such divergent opinions and everything else. And I don't necessarily know that it's any less, that it's any less difficult in Rust, but I think that the values of Rust tend to drive conversations. It feels like there's a keel in the water I mean, it's still the internet, so of course, like it's still like there's still bad behavior and everything else. But it feels so much more constructive because the values for Rust are so clear. So I really there's a lot of value to it. So okay, operating systems in Rust. Finally, the main event. So I would say first of all, if the history of OS development teaches us anything, it's that the runtime characteristics of an operating system trump its development time. Nobody cares how long it took you to develop it. And that it was easy to develop or hard to develop. It's like, no one cares. They care if it works, and they care how fast it is. That's what they care about. And when I say they, I mean you. That's what you care about. You who do not develop OS kernels. And that's what you should care about. It's like, that's what we want. We want it to be fast, and we want it to be correct. And if it was easy for them to implement, great. If it was hard for them to implement, well, okay, is it fast and correct? Yes, it's fast and correct. Like, well, okay, that's someone else's problem. And that's fine. But we have to understand that those are the lodestars. So we can't actually throw those things out if we're going to re-implement an OS in Rust. And we have to remember that structured languages replaced assembly because they performed as well. If they hadn't performed as well, they would not have replaced them. And every operating system has assembly somewhere in it. But with Rust, and I do think that it's important to realize that Rust does represent a new opportunity that we have not had in 30 years more, which is a new programming language that actually is a candidate for this stuff. So the first attempt that I'm aware of is Alex Light's Winix. This was a teaching operating system called Winix that was re-implemented in Rust as an undergrad thesis. The undergrad thesis itself is a great read, where Alex goes into a bunch of the challenges that he ran into as he implemented this. The biggest challenge was that Rust then did not allow for any allocation failure. So if all allocations effectively block or work, or death. Like we all like, why live? Let's just all blow ourselves up. Which is fine. I mean, that's actually not necessarily a bad attitude, especially in user land. But in the operating system, we can't do that. In the operating system, we need to be able to know if this allocation is not going to work, and if we are out of memory, I need to go do some work to free up memory. It's like, well, how can an application possibly free up memory? It's like, well, this application is the operating system. So we've got ways of freeing up memory. Like I will throw out dead processes until we've got memory freed up, which we don't want to do. I mean, this is a definite point of divergence between Linux and other kernels. It's like we actually don't want to throw out dead processes, but there are lots of things that we can go do to free up memory in the system because we control all the memory in the system. So it's very hard to run a modern operating system with SmartOS. Because SmartOS is very hard to run SmartOS out of memory. But we have to be able to still potentially fail allocations in some isolated cases. So one of the things we did in the kernel a long time ago is we introduced the notion of sleeping allocations. Most allocations are sleeping allocations that can fail. Some allocations are no sleeping allocations, which means they don't have that they can accommodate failure. And we need the ability to implement something like that. This is an area that was made much better with the addition of global allocators, which was added, it was like 127, something like that, 126, something like that. But the dealing with memory allocation failure is still very much an active issue, an unsettled area for Rust. I would check out give you the RFC number that you can check out there. These RFCs, if you do real Rust development, you're going to end up in the RFCs pretty quickly as you go to understand, because things are new enough that you're going to be, even if you're using things that are there, you're going to inevitably come back to the design discussions on, and those design discussions can be really interesting and actually uplifting. And one of the things that the way Rust does raw literals, for example, which is with R, the character R, a pound sign or an octothorpe or a hashtag, depending on what generation you are. Which I swear I'd never say hashtag, but now like my kids always say hashtag for everything, so it's like, it's not a hashtag, it's a pound sign, whatever. The R and then hashtag, whatever, some number of hashtags, and then your literal, and then the same number of hashtags as open literal. But just looking at that discussion is a really interesting discussion because everyone's talking about how all these different systems do it. And actually, the absence of raw string literals is a real problem for me in JavaScript, and in C too as well. And it's many, many things that I love in Rust. But that design discussion is really interesting, even though it's a super small issue. These RFCs will get you into those design discussions. This particular area is an area that's still unsettled with respect to allocation failure, but is settled with respect to global allocators, which actually allow you to do a lot of it. Since 2015, there's been this kind of explosion of little operating systems in Rust. If I forgot yours, I'm really sorry. I tried to get them all. I tried to get the ones that still compile. So you got Redux, which is kind of the big one, then Tiflin and Talk and Intermezos and RustOS and QuiltOS and Rux. And then Philip Oberman's BlogOS. Philip Oberman, please give this thing a name. Call it whatever you want. You get to name something. It's like important enough to name it. I don't want to have to call it Philip Oberman's BlogOS. So just give it a different name. It's a great thing you're doing. Like, please, give it a different name. BlogOS, I guess that's what it is. So some of them are teaching systems, Intermezos, BlogOS. Some are unikernels, like QuiltOS, that only are going to allow for Rust programs, kind of limited in that regard. Some are targeted IoT, like Talk. The attribute that all of these systems have in common is they are all de novo. They are all written from scratch, which is great on the one hand, because Rust allows us to explore these new ideas and build these operating systems, and all these efforts should be encouraged, and especially the teaching ones, all terrific. It's great. Two buts on that. One is it means that you're forsaking Linux binary compatibility. And that just means that a lot of the world's software is not going to work, which is fine. I mean, I honor that. I've experimented with that approach for many years. For me, it doesn't work, but I like having the world's software work. And I say that as a Unix operating system that's very, 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 very close to Linux. I'm serious. But like, no. So we've done all sorts of things to allow for Linux binary compatibility. Justin talked about some of those in his talk. That Linux binary compatibility is a really long tail. It's really brutal. It's very hard to do. You end up in a lot of really ugly gray areas. Again, I would refer to Aidan's talk for some of the gray areas that they ran into, and we've run into a bunch. So that you get all those problems, which you don't want to have to go resolve. You do not want to have to deal with vfork and sigchild semantics, trust me. Like vfork semantics, terrible. Sigchild semantics, terrible. vfork plus sigchild semantics, like unspeakable semantic superfund site that no one should have to deal with. And they also means that they are all fighting second system syndrome. They are all fighting like, well, as long as like the train is leaving, let's back up the truck and let's do a new file system. Let's do a new way of thinking about devices, and that can be really productive and interesting, but that can also be paralyzing. So that's a challenge. It's also a challenge. Like, what is the advantage of rewriting things that are actually working code in Rust? And I don't know, because the safety argument just doesn't carry as much weight for kernel developers. Not because the safety argument isn't really, really important. It's just because like it's safe. Because when it's not safe, like it blows up and everyone gets really upset and we figure out why. And we fix it and we develop a lot of great tooling to not have these problems. So it has to have more of a grab than just the safety. The performance is great. There are things that are about it that are great. But this is working code that we want to replace. Like, why do we want to replace this working code? Especially with respect to the kernel, which has multiply owned data structures everywhere. Everything is on many lists. I mean, there are things that are where you've got these nice kind of like hierarchies of objects, but most things don't actually have that. And yes, some of those are semantic sewers and should be re-implemented. Some of them, there are some endemic problems. And you look at like thread dispatch and so on, there are some endemic problems. And then like, okay, well, we're just going to work around this with unsafe. Like, okay, but like every time you use an unsafe in your Rust operating system, it's like you're losing a little bit of the advantage of Rust. But whatever. So I think an OS kernel, despite the historic appeal and the superficial fit, I don't know that that's worth it. I don't know that that's the right first approach. I mean, again, these other operating systems should be encouraged. I think it's great. But I think for the OSs that we're going to use for the rest of our lives, I'm not sure that that's that right first approach. Maybe we'll get there eventually. I don't want to rewrite ZFS in Rust. That's what it boils down to. Like, I wake up in a cold sweat when I think about rewriting ZFS in Rust. And go look at the ZIO pipeline and tell me you want to rewrite that thing in Rust. It's just like, no thank you. I mean, the Rust compiler would slay me. Like, it would win, and I would lose. But let's look at hybrid approaches. So, because I think a hybrid approach is really the right approach here. One is to have Rust in kernel components. So I love the fact that Rust can interoperate with C. So one hybrid approach is that you retain your existing C assembly-based kernel, the way we have had for many years, and then you allow for Rust-based things to be developed, Rust-based drivers, Rust-based file systems, Rust-based in-kernel software. One of the points that Justin made in his talk was that we want to have more in-kernel software. Well, this is a safe way of doing it. Now maybe the safety argument is a big win, because now it's like, hey, more people can safely develop the kernel code. Yes, fine, existing kernel developers are not going to rewrite the kernel, but having a safe Rust sandbox inside the kernel, that might be interesting. It would allow for an incremental approach, which I think, like, let's take that Unix BC approach. And it allows Rust to be used for new development where you're not trying to kind of port existing C structure and being burdened by the C implementation. There's a prototype of this in FreeBSD. Others are possible. I think we definitely want to do this in SmartOS at some point. Hybrid approach number 2, Rust OS components. An operating system is not just the kernel. There's a lot of other stuff out there. There is utilities, daemons, service management, device management, default management, the debuggers, et cetera. Yes, systemd is a part of your operating system, whether you acknowledge it or not. Systemd is, you've got these things that are part of the operating system. These things are great candidates. For like, if you were writing systemd now, no question that it's in Rust. You're speaking for us. If we were writing SMF now, no question in my mind that that's in Rust. That is like, and in part because, by the way, like, let me tell you something that most kernel developers won't tell you. It's harder to write user-level software. It's harder to write user-level software because more can go wrong. Like, do you know a problem that I never have in the kernel? A configuration file that someone deleted. That's just not the way we roll in the kernel. Like, we don't have that. Like, the configuration file is the kernel. Like, if you deleted me, I'm not here. It's not my problem. Like, you can't boot anything. I mean, I got lots of other problems. I got to boot this thing, and then I got like Intel introducing vulnerabilities left, right, and center. I got lots of other problems. I have plenty of problems. But I don't have the problems. I don't have distributed systems problems. I don't have these kind of operational failures. There are a lot of failures that I don't have, and that's the stuff that Rust is really good at. So that might be a really good candidate for Rust. So I think a lot of those are and especially as the OS expands to beyond just an operating system and consists of an entire cloud control plane. And then the third approach, one that I'm excited about at the moment, is there is another operating system out there, an operating system that hasn't advanced technologically as much or at all. That's basically still running glorified DOS, but it's running all of humanity on top of it. And that is this absolute sewer of unobservable, system-critical, mission-critical software called firmware. And firmware has lots of problems, as I'm fond of saying. Like, it is humanity versus firmware, and everyone needs to pick a side. And I think that you look at some of the challenges of the firmware, it's like, oh man, that's a good fit for Rust. Yes, some of the embedded challenges that we have, but those seem much more circumventable. I don't think you're going to have like the multiple ownership disasters that you have in a kernel. You don't have the same expectations around binary compatibility. You don't have to go re-implement ZFS. I mean, it's a smaller kind of a thing. And so when I look at like OpenBMC, I view OpenBMC as on its knees with tears streaming down its face, begging for someone to please rewrite me in Rust. Because if we're going to have the BMC that's going to hang out a socket over the internet, God forbid, or even over the network, I want that thing to be in Rust. I don't want that to be in C++. And there's a lot of stuff like that. So I think that is where I want to see a world. Right now, firmware is the proprietary software that we're all forced to run. I want to see a world where we get to open firmware, and I want to see a lot of that written in Rust because it's a much, much, much better foundation for humanity. We'll do humanity a huge favor. So looking forward, I mean, I'm very bullish on Rust. I'm very excited about Rust. It's something we really haven't seen in a long time. It's a true alternative. We can use it deep in the stack. I think it is. I think we can use it in firmware. I think we can use it in operating systems. I just think that practically it's going to be really, really hard. But I think we can definitely use it in the way we extend the kernel. And the beauty of Rust is that it allows for these hybrid approaches. That the beauty of Rust is its ability to interoperate, cooperate with native systems, with C-based systems, allow for vistas to open up. And for us in system software, it is a very, very exciting time. With that, thank you very much. I have 2 minutes for questions. Any questions? Yes. No, I don't hate it. First of all, I've never felt, I have only tried to bargain with the borrow checker. I have never, even when it is absolutely thrashing me, I know it is out of its own love for what it's trying to do. And I think actually with Rust, it's important to get over that hump. Like, the one thing I would advise if you have not implemented Rust, please, for the love of God, don't start with a doubly linked list. In fact, I wouldn't start, like, it's very often that you I've got the Sudoku thing, or I've got the this solver or that thing that I implemented in every language. I'm going to go implement it in Rust to try it on for size. Don't do that. It's a bad idea. Just because if you haven't seen what the borrow checker can do for you, the first time it begins to fight with you, for lack of a better word. The first time it tells you, and in particular, it will tell you like, hey, I think you want to make that mute. You're like, okay, I'll make that mute. And it's like, oh, you want to make that a reference? Like, okay, I'll make that a reference. Like, no, you don't want that to be a reference at all. No, that doesn't work at all. It's like, I just did what you told me to do, and now I've got like so many more errors. And that's when the tears begin to well up. Don't do that. And one of the things that I did that I would really recommend is, so the 2 books on Rust are terrific. There's, I don't know, do you guys call it triple? I call it triple or turple, all right. The Rust programming language. Steve Klavanik and Carol Govine and the entire community wrote that, which is great, and you want to have that reference. And then the other one is, Systems Programming in Rust? Programming Rust, and the O'Reilly book. And I think that I like having both of those books side by side. One of the things I really like about Programming Rust is there is a fully worked example, and I just like typed that in when I first got into Rust. Like I haven't done that literally since Enter Magazine from back in the day. Like I don't know if you're as old as I am, but like you're like opening up to the back of Enter Magazine, like typing in your basic on the C64 or whatever. It was really valuable to do that because you'd have typos and then you'd fix them, but they'd all be very gentle typos. And you know that you've got something that's correct. And by the time even I'd gotten through that simple exercise, I'm like, okay, I see the value. So when the borrow checker began to torment me, I'm like, I know this is out of love and not hate. Because it can feel confusing. Other systems don't have ownership. And this is a novel thing about the system. I think the community does a great job of doing this, but just to emphasize this, with Rust, you need to learn it. And if you are of the age where you're learning lots of stuff, that's easy. And if you're of my age, where it's like, I've been able to kind of like wing it by just like pounding stuff out for a while, it's like I need to go back in time and actually buy the books, sit down, read the book in a quiet place, really understand it, read it again, read another source. But Rust rewards that. It rewards that education a lot. Long answer to the question. Yes?
At the beginning, you said that terminal illness for Multix is that PL1 compiler did not exist for 3 years. Rust, do we now have a Rust compiler, an optimizing compiler, where this at the same level where GCC and Clang now do for similar?
So I'm a latecomer. So for me, yes. Because I haven't lived in this kind of tortured past where I think there are people that used Rust 2 years ago were like, oh my God, never again. And because they, whatever, because it was early. For me, it's been great. And it performs well. It generates, I think the incremental, when was incremental support added? Early this year. So like that's not that long ago. Like to me, that's always been there. So it's like, no, like, why is everyone complaining about the compile times of Rust? Like, this is great. It's like, because, like, just before you showed up, it was a serious problem. That's why so like, things like that, like Rust is really solidifying, I think, quickly. To me, I would not hesitate to use it for production software. I mean, it's because I'm ignorant of the very recent past. But, whatever. I would not, I think it's ready. Yes?
Is there a benefit to waiting a little longer, say another year?
Sure. I mean, I think that there is, and I'll tell you, a couple of the benefits will be that I think Rust is a big deal for system software, and I think waiting for another year is going to give you that many more resources to learn from. It's going to be, the documentation is going to be that much better. The crates are going to be that much better. You're going to be that much less likely to get into the RFCs. I mean, you're going to have non-lexical lifetimes in a year, right? Okay, December 6th. December 6th, perhaps, of 2025. But you're going to, and if you use Rust after non-lexical lifetimes integrates, you're not even going to realize what the fuss was about borrowing checking. You're like, why does everyone like complain about the borrow checker? Like, I've never had a problem. It's like, because right now, Rust really only uses lexical lifetimes. And there are times where you're like, no, seriously, Rust, I swear, I'm done with this. Like, look at the code with me, Rust compiler. Like, we're done with this. And it's like, well, no, I only use lexical lifetimes. When you have non-lexical lifetimes, which is in nightly, and you can enable it optionally. December 6th is going to integrate December 6th? We're shipping on December 6th. I don't care how broken it is, we are pushing it on December 6th.
We have been polishing this entire thing called an edition coming out, which is how we're versioning compilers, which I won't get into. But we have been planning on shipping it all
Right.
year. Polishing it all year.
That's going to make a big difference. And again, that's going to make a difference that you literally won't even be aware of. You will just not understand what the fuss was about the borrow checker. I think. I mean, I don't know if you guys agree with that, but I think it's going to make a big difference.
It makes the error messages better at the same time.
Way better error message.
Right. So and gives you high quality artifacts and everything else. So yeah, I think I mean, this is not like a hey, do this. I mean, I honestly think Rust is going to be around forever. I really do. I think this is like this is the formation of ancient Greek. So I mean, there's no rush. You got thousands of years. I mean, there's no like take your time. And it is going to get better. But I also think if you've been waiting because things are too crazy, you don't need to wait that much longer or don't need to wait at all. All right, with that, I think we're done. Thank you very much, Justin.